Hello, everyone. Let's have a seat. And now it's time for the next presentation. We have a guest from the Netherlands, Dr. Simona Bianchi. And she's a postdoctoral researcher and also instructor and lecturer in Delft University of Technology. She has a PhD from structural engineering from Sapienza University of Rome. Now, but she is teaching in Faculty of Architecture in TU Delft. And also she has an expert on the topic of earthquake engineering. And today she will present her speech entitled with Low Damage Resilient Technologies for Seismically Safer and Sustainable Buildings. And she has also involved some research projects funded by European Commission, and also she has several research papers related to this topic. And now I would like to invite her to the stage for giving her speech.
Thank you so much for this introduction. Yes, indeed, in this second, let's say, seminar, we will completely change the topic because we will be looking at some technological solutions for creating indeed safer and sustainable buildings, because that's possible. And actually perfect in line with the title of your event, this is Shaking Boundaries. We will also have a look at some shake table tests I perform on these technologies, like this one. Okay, you heard the sound. It's good to hear the sound, but also the building which is shaking. Well, in the meantime, I can describe you what you will see. That was actually part of my PhD work. Here you will see this big shake table that we use for simulating earthquakes. So if you want to check if a technology is earthquake-proof, earthquake-resistant, you will see that for me, they are two different words. We use this, let's say, kind of testing apparatus. And in this case, I was simulating the Christchurch earthquake, the earthquake that happened in 2011 that completely destroyed the city. That's quite a big one because we have 5 points, let's say more than 5 meters in and 6 in the other one. And here, as I was mentioning, we were simulating the Christchurch earthquake that happened in New Zealand. And this completely destroyed the city of Christchurch in 2011. While in this case, we designed our specimen to be earthquake-proof. And you see there's no damage after this earthquake with more than, let's say, 6.3 magnitude. Now, I already had a very nice introduction, so I can also skip this slide. Indeed, I studied in Italy. And let's say during my I had a lot of experience, as you can see here, both in academia and industry. And also I spent a period in Christchurch where I learned a lot on these low damage technologies. And indeed, our presentation for today will focus on these solutions. First of all, I want to describe you what does it mean to follow a so-called damage control design philosophy. And we will have a look at this technology for both structural systems, you know, when we focus on the frame, wall with beam columns, flooring systems, and so on, but also non-structural components. These are very important because they can represent a high percentage of damage after an earthquake. Now, starting with a very brief introduction. Well, you know very well what are the devastating effects of an earthquake, right? Well, as you can see here, our buildings are very vulnerable, which means I do have a lot of damage. I have severe socioeconomic losses. And also, if you think also the environmental impacts I can have. What's the problem? So how can we rebuild our cities to be safer? Because as you can imagine, most of these buildings actually they are so damaged that it's impossible to repair them. It is better to demolish and rebuild them as new. But we need to find solutions to do so. let's have a look at our, let's say, current code compliant procedures. This is what we typically do in earthquake engineering, which means we design, let's say, our buildings following the so-called performance-based seismic design. So, for example, this is a design matrix. We do have different levels of the earthquake. Where I move here, it means that I'm increasing the intensity of the earthquake. And I'm, let's say, designing my buildings based on the performance that I want to achieve. So, for example, I have this intensity level. My building will be safe, which means I want to target life safety. I accept the damage because my objective is to have buildings that are able to sway while people can evacuate after the event, during the event, actually. So you see, if I have a very small earthquake, I want my building to be fully operational, which means after the earthquake, there's no damage. I can go there and use my building without any problems. So based on the, let's say, intensity, I do have an increasing acceptance of damage. This is what we typically do in seismic engineering. Because in the end, also damage is contributed to dissipating the energy and so on. I can have also a reduced cost of my building, so it works well. Problem is this enough nowadays? So we saw all those damages. Are these acceptable in our modern society? That's not the case. So this is what we will have if I design my building following the codes, the standards. This is what I expect to have. As I was saying, we are able to design where I have damage in my buildings, in which locations, and what to expect after the earthquake. And you see a lot of damage to non-structural components like facade, ceilings, partitions, and so on. This is not acceptable anymore because I want to improve my design. I don't want to accept anymore all this damage. So nowadays, we need to have a high-performance building which is earthquake-proof, which means moving my, let's say, design objective toward a higher performance indeed. After, let's say, low to moderate intensity earthquakes, I want to have my building already fully operational. After the earthquake, I want to go there and directly use my building again. In case of, let's say, a moderate and too high to a stronger earthquake, I want my building to be operational, which means I can accept a bit of damage, but not so severe. It doesn't make any sense anymore because we want to improve the resilience of our buildings. Is this acceptable by the code? Yes, it is, because as you know very well, a standard, they provide you a minimum by law, but you can always do better. Like when you design a facade, you consider a specific transmittance value, but you can always improve, let's say, all the layers and achieve a better performance. And the codes, indeed, they are providing us with a lot of indications on how to create these earthquake-resistant structures. Earthquake resistance, which means I need to have a specific construction detailing in my beams, in my columns, to have a proper design of the rebars inside to create specific mechanisms and so on. For example, here you see some of these technologies highlighted, the other ones, apart from the traditional solutions, like bracing systems. So I want to improve the behavior in case of this lateral loading on my building. And also some isolators. So in this case, what I'm doing is, let's say, concentrating the flexibility here while my building has a reduced seismic demand. So, they work very well. But what is the problem? They are not earthquake proof. Because earthquake resistant, it means that after the earthquake, I still have damage. It's part of my design. Nowadays, we are expecting an earthquake-proof buildings, which means I want to have a negligible damage. And this is possible to achieve. Now, I will focus on specific solutions I've been working on for my PhD and also postdoc. For example, here, this is what we expect in case of seismic design. So this is the so-called plastic hinge that is forming in this corner along the beam. This is very good. If you look at this and you think, oh, it's perfect. This is what I designed my building for after the earthquake. But I want to reduce this damage. Let's have a look how this can be possible. For example, in the last decades, there have been a lot of studies focusing on this solution. And this is one of, let's say, that I'm especially considering in my studies. So you see, it's called the precast seismic structural system. How does it work? Well, you do have, in a, let's say, traditional system, you have your column, your foundation, and these are connected by means of rebars here. Here I have my column, I have my foundation, and this is a precast, a prefabricated column. So you see, and the connection is made by means of this internal cable and these external devices. What are they? It's like a steel rebar. And why this? Because imagine you have an earthquake. It works like this. So during the earthquake, you have this self-centering capacity. That's very important because you come back to the initial position, the initial state, and you have a lot of dissipation of energy in these devices. So it means after the earthquake, in the previous case, I do have all those damages on my beams, my columns, while in this case, I go there, I simply change these ones for a cost of 30, 40 euros only, and my building can work as a new. So I concentrate the damage into these devices. And because of, let's say, the simplicity of the concept, actually, this can be designed. We do have also some guidelines that have been developed also for designing. So, for example, this is the behavior that we currently use to describe the tendons. And you see they have a kind of elastic behavior, while in this case, these are my devices, these steel rebars. And they dissipate the energy, which is represented by this area. So I can, the combination of both is what we call flag shape hysteresis loop. So I don't want to go into the details, but that's very easy because I can really design. For example, I have these rebars, what is the internal force, the dimension, the diameter, and so on, based on the dissipation capacity and based on the response that I want. And the same concept can be applied to all the different components within my frame structure. So here you see an example of wall. This is, again, what I design following the code, following the code, while in this case, I'm using this new technology. Energy dissipation concentrated here, which means I'm only, let's say, damaging these components. I go there after the earthquake, I change it. I change them. While here, I do have a lot of damage at the base of the wall. So I want to avoid this. Now, it's funny to see that we take a lot of inspiration from the past. And in this, you can also see this first concept here, you know? For example, these temples from Greek or, for example, Roman temples. Well, in this case, we do have these marble blocks, and they have the heavy weight, so that there's not a cable inside, but actually you have a lot of weight due to the blocks, due also to the roof, and they act as a vertical loading, which enables to have this rocking movement, self-centering capability. So you see that's very nice also example on how, let's say, we take indeed a lot of inspiration from things that work well in the past. Because of let's say, the facility, the convenience, and also the potential of this solution, there have been already some application in real buildings. And as you can see here, I was mentioning before that the Christchurch, the city in New Zealand, that was completely destroyed after the earthquake. And indeed, they rebuilt structures by using this technology. Here you see the first so-called, to use the acronym, press building that we have there. But also in San Francisco, you see some examples, actually. So in America, New Zealand, and now we are trying to bring also this new technology in Europe. Now, what is the nice thing is that the solution, the concept is very easy, that can be applied to whatever type of material. For this reason, we have, let's say, an extension of the concept also to timber buildings, to steel structures, to mixed, maybe timber concrete structures. And for example, here you see a specimen that was built in Italy. And here we can understand also how it works, this connection.
Prossimo test S3, 75%. 3, 2, 1, inizio test.
So you see what is happening during the earthquake. There's an opening of the gap in the contact between our beam and column. And let's say the dissipation is concentrated into these devices. So as I was mentioning here, it's like a steel rebar, and you have an internal kind of fuse. Well, here you see these tube for anti-buckling. There's mortar inside, but everything is let's say, the dissipation is materialized here. Now, there's also a nice thing. These solutions are very rapid to build, very fast to build. Let's see this example. So here, again, is the same specimen that was built again in Italy. We start by building them on the floor, and then we uplift them. We start by connecting all these components. We put the floor in place, and then you see we are day 2. It's very fast, it's very rapid, this erection time. And that's very convenient. The solution is flexible, modular. We have plug and play connections. It's kind of a Lego system, you know? So imagine this was for a specimen in the lab, okay? But the same applies to whatever type of real structures. And indeed, again, a lot of new buildings, in this case, focusing on timber, again in New Zealand. And it's also quite nice because of the aesthetic. You can also maybe, you walk along the stairs and you see, oh, this is the dissipator. Do you know how they work? And so in terms of awareness of these solutions is also very nice. Also here, you see in this office. So for example, these are other types of dissipation, let's say, devices. These are called the U-shaped flexural plate. You will see an example later on. And here you see the internal cables. So you see here, they put a glass, especially because they wanted to show, you see this building is earthquake proof. Now, what is the other problem? Is that, as I was showing at the beginning, within our building, there's not only the structural skeleton. We do have no structural components like facades, partitions, ceilings, and so on. And actually, if we look at earthquake reports, especially in case of low to moderate intensity events, they actually highly contribute to the damage. So look at this. Structural parts, 25%. All the other components, well, actually quite a lot of percentage. What does it mean? That we need solutions also for the non-structural elements within our building. And for example, let's focus on the facade. So let's imagine you have a low intensity earthquake. Well, maybe you say, okay, I have damage in my silicon. There's a bit of degradation, which is okay from a safety point of view. But how about the functionality of your facade? So you design the facade to be for airtightness, for water resistance, and so on. So it doesn't work. You invested a lot of money in that solution, but it doesn't work in the end because of this very small vibration. Therefore, in this case, also we have a lot of solutions. But first of all, we need to understand how do they behave in case of earthquakes. So for example, here, very simple concept related to the facade. You do have so many different detailing. For example, infill systems or cladding walls connected by means of connections, or maybe monopanel, multiple panels in the vertical, horizontal. Why this is important? Because based on that, I can understand what are the damage mechanisms that can happen, and I want to avoid those damage mechanisms, or at least reduce, minimize the damage. And also in this case, we follow the same approach. We want to design for a specific performance to be achieved. And here, let's have a look at very simple sketches on these solutions. This connection. So imagine you have an infill wall, which is connected to your frame structure. What is happening is that you have a lot of stiffness. So this can be avoided by simply making a disconnection. You create a gap. In this case, you avoid the interaction between the structure and the facade, and this can reduce a lot of damage on the component. Or other systems. You want to improve the connections. You use lighting connections or dissipation, or I want to improve, to strengthen, let's say, my wall, and well, a lot of techniques. And indeed, for especially my PhD, you will be looking soon at one of the experiments that I performed. I was focusing on these solutions for non-structural components. And actually also during my postdoc, focusing on curtain walls, for example. So here, monolithic wall, as I was mentioning before, it is a matter of disconnecting the wall from the structural system. I want to avoid this interaction. I want to create these walls with gaps. So in the end, they have this rocking movement during the earthquake. The same applies to a traditional gypsum panel. I can follow the same approach. I'm only, you know, changing a kind of some detailing, cost-effective detailing, cost-effective solutions, and in the end, I have a very, let's say, performance solution. That's fundamental to achieve in our concept of integrated earthquake-proof building. Then, also here, cladding systems. Well, for cladding is a bit different because I do not have an infill panel. I need to rely on the, let's say, dissipation provided by my connection devices, which means I need to improve the connection detailing, connecting, let's say, the cladding system to my structural system. For example, here, you see an example. Let's go directly to the video so you can understand better how this works. So what is happening here? This is the so-called U-shaped flexural plate, as I was mentioning before. And everything is concentrated here. You can reduce the acceleration and force on your cladding. So in the end, you concentrate all the responses here. And the nice thing is that this connection, so if you consider a specific connection by means of steel plates, typically when you achieve a certain displacement on your building, they expect to fail. Well, in this case, it is related on the kind of a fatigue criteria, which means how many cycles you have here before they can fail. And this is a huge number, like more than 150 cycles or 200 cycles. That's one of the concepts, just to show you an example. But again, curtain walls, spider glazing, unitized curtain wall system. I've been working on that for my postdoc. There are solutions, which means, again, I want to achieve a certain behavior, rocking, sliding. Based on that behavior, I design my connection detailing. I design the connection between the components. You know, for a facade, it's kind of complex for a glazed facade because you have the glass, you have the connection with the frame system, and then you have the frame system connected to the main structure. So there are a lot of components which can contribute during the in-plane movement, and all of them should be considered in terms of behavior, and I need to improve this connection detailing between the components and to the structure. Also ceilings, well, that's also a very easy solution, but sometimes we forget about this. So if you have a ceiling with this gap all around, actually you can have a pounding effect. There's a lot of acceleration, and this can cause a dislodgement of the panels of the ceiling. That's not good because maybe there's a person, so you can cause injuries or well, within the building for occupants. So what we can do is very simple concept. You put an elastic isolation foam, and in the end, you can avoid reducing kind of this bounding effect. Now, why I'm saying this? Because let's say that for our structures, especially in earthquake engineering, we work a lot with kind of some curves, which we call them fragility curves for describing the damage of our components. So you have your, for example, in this case, it's a gypsum panel. Well, in this case, we have these three curves, each representing a damage condition I can achieve on this panel. So here, the first one means I have screws pop out, minor cracking, it's light damage. The second one, moderate damage. This one, heavy damage. And let's have a look at what is happening when I apply this low damage detailing. I move these curves towards the right part of my graph. Why is this important? Because let's suppose you have an earthquake. So this earthquake, from my simulation, I do understand that I have a certain floor displacement. From this floor displacement, I can identify the so-called story drift ratio. And I see, okay, here, that's my building. Let's have a look. So here, I have 100% probability of my traditional component of experiencing this damage. While in this case, I have 80% probability and so on. Let's have a look at the low damage components. So here, in this case, I'm moving toward the right part of the graph, which means I do have only 40%, a bit more, let's say, probability of being in a slight damage, which means my components are able to withstand higher seismic demand, in this case, in terms of displacement, which is very important in case of vertical components like, for example, facades or partitions, while the same applies to ceilings, where the main, let's say, stressor is the acceleration. And That's fundamental. As I was mentioning, our goal as a researcher, as a, let's say, for the scientific community, we want to create an overall whole low damage integrated building. Now, I was showing some, let's say, results from the lab, but I've been working a lot also in terms of numerical simulations. Well, I don't want to go into the details, but why this? Because in the end, I want to quantify the convenience of this solution. As you can see here, there's quite a lot. So what are these graphs highlighting? That when compared to a traditional solution, I can have a lot of savings in the building lifetime. So there's an example. These are from calculation, seismic analysis, loss modeling. Again, I don't want to go into the detail. But for a 5-story building, after this calculation, you can understand that in your building life, you can have this huge amount of savings. So you see how much that can be. And the same applies to the downtime. What is the downtime? After an earthquake, you have damage, which means you have a post-earthquake inspection, let's say contractor mobilization, a lot of delays, and then you start with the repairing actions. Well, this is called downtime. And in case of low damage solution, because of this very slight damage, in the end, negligible damage, this can be reduced quite a lot. So I can have a reduction in terms of months if I apply these solutions. Because as I was mentioning before, I have my dissipator, I go there, I change them. That's very easy and fast to be done. Now, let's have a look again back to our, let's say, whole building as I was showing before. Because based on this concept, as part of my PhD, indeed, I wanted to study a bit more. And I've been involved in this European project, which is called SERA, where there are a lot of partners who were involved and so many, but in the end, it was coordinated by Sapienza, especially myself and a colleague. We were leading this project. And we focus on these 3 configurations. So of course, first of all, we want to understand, okay, what is the behavior of our low damage structural skeleton first? Then we started by including non-structural components like here, partitions. And then we moved to an overall configuration with facades. As you can see here, we do have glazed facade, precast concrete, and internally there's a masonry wall. Now, first of all, you design the specimen. So here you see all the dimensions. We do have, indeed, it's quite a large structure. It's a half-scale structure. So it's like a real building, but you consider half size. And well, in this case, it was a mixed concrete timber structure. Indeed, we do have, for example, here concrete walls combined with this timber wall with CLT. And then we had also timber beams with, let's say, the 2 floors that were kind of a mixed timber concrete flooring systems. And as part of the design, of course, these are, you consider, let's say, a prototype building, and then you extrapolate a part of that and you realize your specimen. At least this was the concept that we adopted for this. Considering a specific intensity zone, because you need to consider that in your design. There are calculations methodologies, and so also for, let's say, designing the dissipators in terms of dimensions, the post-tensioning properties, etc. And here you see some of the detailing. So we design all of them. That's important because right now we have been focusing only on the dissipation. Look at how many in the end the plates we do need, and all of them should be verified. We need to follow in this case, the Eurocode was considered. So detail between the beam and the column. The beam is sitting on its shear key, and here you see the dissipators. So the same applies at the base of the column, where you have the concrete column connected to this. Well, it was a steel foundation as part of the lab. And then here, other detailing of the post-tensioning timber anchorage system on, let's say, on the column at the top, on the top of the wall. Now, funny, was funny because in the end, all these components, they were prefabricated in Italy. And then we put all of them together on a truck, and they were moved to Lisbon, where we implemented, we conducted the experimental testing. And indeed here, you see all these components, and then they arrived in the lab. Here was the National Laboratory of Civil Engineering in Lisbon. You see the steel foundation. Here we started with uplifting. So we follow a different approach. Before we saw all these framing system on the floor, and then we started by uplifting them. Well, in this case, it was kind of the opposite. We started by erecting the vertical components, and then we move on with the horizontal components, and we finalized with the flooring system. And then what we did with the crane, we put the specimen, this overall structure, and then we move it to the shake table. And the same applies to the non-structural components. So I was mentioning before, very important to consider them in our design. And here you see some of the detailing, which means including seismic gaps, or maybe, you know, very simple. Sometimes in a traditional way, we do have screws in both directions. Actually, if I keep only these in this direction, I allow more movement of my system. And here again, there's the real construction on the wall where you do see the internal gaps, the gypsum board on these connections that were connected by means of male-female joints and so on. I do not go into the details. And the same applies to the low damage masonry walls. So I was explaining before the concept, okay, instead of having this monolithic wall with a bounding element like the mortar connected to my overall structural system, I include seismic gaps, which means I divide my wall into several parts. And in the end, they are free to move during the earthquake. I can achieve a very high floor displacement before having damage on my components. And here you see, again, these detailing. Then we also tested that's a so-called glass fiber reinforced concrete cladding, where you do have indeed fibers within the concrete. There's a technique by means of a spray to create these components. And they are connected to this, let's say, steel frame system, which is interconnected to the main structure. Like here, maybe you see here, let's say the connection on the bottom part, and here on the top part by means of these sliding connection. So you have this kind of steel tube, which is supporting the facade. And it's very easy because it's very fast and rapid to assemble. Also, the spider glazing. Well, in this case, we didn't focus on unitized curved wall for this specific experiment, but spider glazing. Well, in this case, there's the spider connector. I have to say that this solution already works quite well in case of earthquake, but you can kind of improve a bit the connection of the spider connector to allow more movement, more tolerances, and to design them in a certain way. But the solution works well because it has an independent behavior when compared to the main structure. So it's just a matter of properly doing adjustment at the connections. And here you see all the specimens that were tested. Actually, we carried out more than 150 earthquakes on this shake table. And in the end, you will notice that we had slight damage. Now, as part of this design, also sensors. You know, when you do experiments in the lab, you do need also to capture all the movements, for example, displacement, accelerations, and so on. And this can be done by using a specific instrumentation. And it's very important to design this monitoring system very well. So in this case, look at the large amount of sensors that we consider. Around, well, the maximum was 78 because we had to arrange considering all the different phases. And also this was due to the capability of the testing lab, actually. You can have even more. But what you do is to concentrate them in the points where you want to monitor certain behavior. So for example, here at the beam column joint, these are, let's say, transducers. They monitor the opening of the gap I was showing before in terms of displacement. We do have also a load cell here to understand let's say, to monitor the force that I have on my cable inside. We do have accelerometers on the wall to understand accelerations, and that's very important in case of non-structural components. And we selected these earthquakes. So you see all of them here, and Well, what's the point? When you design an experiment, you do consider a few earthquakes, which means not, let's say, 100 and so on, but you do a lot of tests because you increase the intensity of the earthquake. So you start with a very kind of a small intensity. Let's say that just to explain a bit more, for each of these earthquakes, you have a specific station where you can take these records. Like the real earthquake that happened, for example, again in Christchurch in 2011. Well, what you do is then applying a kind of a scaling factor. I want the same earthquake to be with a lower intensity, then I want to increase the intensity and so on. And typically you select a lot because of each earthquake has its kind of range of frequencies that can have a different impact on your building. So these are the events that we have been, we selected. And now let's have a look at the results. Here, 7.1. That's, let's say, Darfield, again in New Zealand, which is a very high seismicity zone with so-called peak ground acceleration 0.35 G. And here you see maximum interstory drift. As I was explaining, that's a very important engineering demand parameter that we consider in earthquake engineering, which means you have the two floor displacement between the two stories. You take them and you divide it by the height of the story. Now, let's have a look at the first one. Now, again, another example, well, in this case, there's Christchurch, with it's a different type of earthquake. It's a near fault. The previous, you typically have kind of far field near fault earthquakes. Well, in this case, we consider Christchurch. Here, the focus is on the second configuration where we had this partition wall. You have a shake table which enables you to move in just one direction. In this case, you have a 3D movement. So you can apply in both, let's say simultaneously in both directions and also vertically. Very important. Now, I think it's very nice to see from kind of an internal camera what can happen. Here the earthquake, so this is the signal. There's the acceleration over time. And here you have this signal. And again, last one, focusing on the masonry wall. Do you see damage? Any severe damage? Because of the detailing that we have considered. Indeed, let's have a look at what we noticed after these earthquakes events and also all the testing. Structural system. After, again, 150, actually 200, because in addition to these earthquakes, there are kind of, we call them white noise signal to understand what is the variation in terms of natural vibration of the structure. So you do a sequence of earthquake and then you understand how these can vary. Look at this, damage to the dissipators. Well, actually, this is what we expected. We designed the building to have damage here. We wanted to concentrate. These are like fuses let's say within our system. Other damage, a bit of pounding effect because of we noticed, okay, we had to improve a bit the connection between this flooring system and the beam. And then also these, let's say, kind of deformation of the plate was due to the vertical movement, because sometimes, you know, we forget about this vertical acceleration, which can be very impactful. No structural components. That's the only damage we observed after the whole campaign. Let's have a look together. A bit of damage to the kind of cracking starting from the doors. So here, well, we need to improve this detailing, I know, but it's not so high. It's kind of a slight damage. You see all these lines. Actually, I was going there and kind of understanding what are the dimensions of these cracks and also drawing them on the wall. A bit of misalignment here of the spider glazing. And again, we only notice one brick with this damaged horizontal crack. So after all those earthquakes with quite very high magnitude levels, this was the damage that was observed. Therefore, I have to say that was very good as a kind of test to really show the potential of these solutions. But we need to advance with our research, because nowadays there's not only earthquakes. We indeed have other extreme events, like, for example, climate-related extremes, which are becoming more frequent and severe also due to climate change. And indeed, I'm now focusing on kind of combining this detailing for earthquake-proof building with other detailing for a multi-hazard resistant structure, focusing specifically on flooding and heat waves. And another problem is that, well, nowadays, everywhere all around the world, there's this idea of improving resilience, but in a sustainable manner, which means we want to use nature-based, bio-based solutions. Therefore, again, focusing on these earthquake-proof systems, combining them with a kind of multi-hazard scenarios, because our real structure will experience different hazards. We are looking at technologies capable of resisting to all of them, but also kind of involving these nature-based kind of either layers within a wall, or maybe trying to look at kind of not only a sustainability by design kind of approach by means of these modular, flexible plug-and-play systems, also considering specific materials that can be used for these solutions. Because, today I've been focusing a lot on experimental testing technologies, but always, as always, we also do numerical modeling to understand and simulate the behavior of our components, of our structures. And we do have also the capability of quantify what is the environmental losses in case of an earthquake. Because let's suppose you do your model. From your model, you can quantify the damage. If you have a damage, you can understand what are the repairing actions that you need. And these repairing actions, they can cause a certain carbon emission. You can quantify them. And by means of these low damage techniques, we are able to reduce by 40% these carbon emissions, because of this negligible damage and associated repairing costs. Now, why I'm saying this? Because, well, a lot should be done for new buildings, but a lot should be done for existing structures. Indeed, again, today I was only focusing on new builds, modern buildings, how to improve kind of our code compliant approach, what we have been doing in research and so on. But focusing on existing structures, they are very vulnerable. And indeed, we are trying to apply the same concept to those. Here is an example, well, by means of external low damage exoskeletons, because the advantage is that in this case, of course, it depends on the solution. If you have an isolated building, that this can be easily applied. If you have this exoskeleton system, imagine you are not only providing a structural strengthening, but you can also work on the facade. And in this case, you can improve maybe resistance against earthquakes or resistance against heat waves or flooding and so on. You can work on both. Sometimes that's not enough, because you need to integrate maybe more specific solutions for the structural strengthening and so on with the local intervention, maybe global intervention. But again, let's try to minimize the impact on the occupants, because we need to try to reduce this as much as possible. For this reason, the exoskeleton is a kind of low invasive solution. Although, again, sometimes that's not possible, there's not enough, it should be integrated with some of them. But also here, if I want to create an external wall, why not using the low damage technology? And I want to leave you with this also these concepts that, especially now within a specific project I am coordinating, in addition to earthquake-proof sustainable solutions, integrated technologies, again, focusing on both the structural system and the building envelope. We need to consider both if we really want to have a solution which is energy efficient, safe, sustainable, and resilient. Okay, that's all from my side. So hopefully, I'm sorry again if I didn't go into the detail of each section, but I wanted to give you a kind of an overview of the work I've been doing on these low damage techniques, starting with damage control concept, moving to the low damage components for both structural systems, non-structural components, and their integration into the creation of these integrated earthquake-proof building. Thanks a lot.
You are giving lectures in core studio, computation, earthquake, resistance. And so I wonder, how do they integrate the computational design tools with those topics related with earthquake assessment tools? Maybe you can mention about the student projects that is more related with these topics. I wonder how do they deal with
Yeah, it's a very nice course that they started last year. Actually, it's quite recent. Actually, last year they started focusing on earthquakes, and they will continue working on them. There are so many different projects because each student they decided their own topic, focusing on these kind of technologies. What they typically do for connecting with computational part is creating a kind of, is developing a parametric design for these solutions. So they work with Grasshopper, these tools, to create a kind of a digital workflow to optimize, let's say, the design of these components. So we have been focusing on both mostly the structural system because of the interest of the specific students, but some of them, you will see actually, I don't know if most of the students will join tomorrow afternoon for the workshop. There are a lot of workshops on some of these topics. One of them also focusing on facades with curtain walls. And let's say different students, they decided also to move on with their graduation project on that. So in the specific case of curtain walls, for example, this group, they focus on creating this digital workflow to improve the behavior of the shear walls within the building and to understand the impact on the curtain walls. Is mostly, let's say, related to the technology part optimization and the application indeed of kind of, some of them also, they create a kind of archetypes, machine learning technique to create surrogate modeling, understand the behavior and how to extend at the urban scale. Other ones indeed focusing on risk. So today the lecture was about technologies, but I am kind of split in two parts because I work also on risk assessment. Well, in this case, they have been working on identify, let's imagine you have Izmir, kind of the map, the digital map, to identify where you have more risk in case of an earthquake, to kind of visualize this by designing, by showing the building kind of in a heat map, to understand where you need to improve and to kind of address the intervention planning. So there are so many interesting and so many different projects today. But yes, mostly, let's say, large scale analysis, simulations on a building level, connection with the parametric design and optimization if we want to focus on the building. Yeah.
This is what I wonder. Actually, you mentioned about some hands-on tests. You are also working in laboratory for hands-on tests, like using shake table test and so on. I wonder what kind of simulation tools they are using to assess earthquake damages.
There are specific, let's say, software for that. We use in structural analysis. So, for example, during the course, I show them how to create a model and how to simulate the earthquake and to understand if the building is behaving as we expect or not. And based on that, we need to maybe include some retrofitting intervention if it is an existing building. For example, one of the group, they also focus on an existing school building in Turkey. I don't remember now the exact location. And they design a retrofitting intervention using damping devices. So not this solution, but another one. So they created the model. There are so many different softwares. I was showing them, well, just for you to know, in kind of OpenSeas, sub 2000, if you want to move toward kind of a simplified. Also within actually Grasshopper, some of them, they work with Alpaca, which is connected with this OpenSeas, and you can create your model. You can implement the structural analysis, the seismic analysis. There are different techniques. And you use this outcome for improving either the behavior or, I don't know, understanding the risk that you might have in case of a low to a strong earthquakes and so on. But yes.
Great. Thank you very much, Simona.
You're right.
Okay, there's one question from Dr.
Thank you very much. I hope our students are going to ask questions as well. But again, thank you for your presentation. Well, I wondered about one independent variable in this test, which is the change in the land characteristics. For instance, I'm living in Izmir, very close to seaside, and I just realized that in 25 years' time, the fluidity level in the land is changing a lot. Maybe this may not be your focus in your experiments because it's very extensive to consider all the aspects in that sense. But at least I wonder, for instance, in applying all these mock-ups in real conditions, to what extent can you, consider these changes in land or the kind of fluidity? This may affect maybe the lateral forces of the earthquake.
Yeah.
So I'm just curious about that. Thank you.
No. That's indeed not the specific focus, but it's very important because you can kind of understand how indeed mostly the forces that you experience at the different floors, they are impacted by the soil properties or the conditions that you have. So in these experiments, actually, what we did was selecting a specific soil type and considering, let's say, these acceleration time responses adapted to reach a specific response spectrum that we consider. So we follow a kind of spectrum compatibility approach, but considering only targeting a specific soil type. But it's very important to understand that this soil structure interaction and how these can potentially affect indeed the overall building.
So can we say that these applications may be region specific, for instance, when you did it?
Yeah, unfortunately, yes, because as you know, that's very dependent on that. Kind of the local scenario is impacting a lot the result. We try to select high seismicity zones in Italy, where we expected to have at least following the code for the soil category and classification, the same soil type. So although we had variations in terms of frequency and behavior of the signal and so on, we tested all of them on the same soil type, but in kind of different locations. But yeah, that's true.
Thank you for your presentation. It is very informative for us because a couple of instructors, we are working on a project focusing on damage of non-structural elements. But I'm just trying to understand the damage of the structure. And you use different two materials, timber and reinforced concrete together. And I'm just guessing that after 50 years, the behavior of these two materials will change for the resilience, right?
Yeah.
And did you search or work on it?
Yes. Well, I'm now, I'll be showing maybe tomorrow a bit. I'm now coordinating a project which is called MultiCare. It's a Horizon Europe project focusing on multi-hazard low carbon resilient technologies. So quite a long title indeed. And let's say the kind of degradation of materials, it's important when we want to quantify also resilience. So what we typically do is focusing, but from a simulation point of view, numerical point of view, I've been working on that. So what we are achieving is identifying a way for quantify the resilience of the buildings in their lifetime, and to understand what might be the effect of different, not only earthquakes, but other disasters that can happen. And indeed, the kind of the response over time of the materials, but of the overall building, the facade and so on is very important, because at the beginning maybe is 100 functional. In some years, we have already a percentage kind of functionality drop, and we are considering them within our simulations. So not from a kind of an experimental point, not yet, at least, but simulation, yeah, absolutely.
Thank you.